Today we're going to talk about directional derivatives and gradients, and I don't think I fully, completely derived the directional derivative formula, but I'm not going to anymore, so I'm just going to give you the formula. It has something to do with the run being equal to 1, and so we make it into a unit vector. Maybe I should just copied it from the book, but oh well. So it's going to go something like this. The formula for the directional derivative. So the derivative of f, and let's say f is a function. We'll start with R2 to R. So I'm hoping that you're getting comfortable with this notation, that whenever you see something like this, you know that this is a z is equal to f of xy type of function. And then if this is a 3, R3 to R, then it would be a w is equal to f of xyz. It has 3 variables. But here, we'll just do it with 2 variables, and then it's just going to extend to 3 variables later on. So a derivative of this function at a point doesn't have to necessarily be at a point, but usually when we're talking about directional derivative, we're talking about at a specific point. And then for directional derivative, you need a specific direction that you're going towards. The partial derivatives are special directional derivatives where you're going along the x and along the y, along your whatever the independent variables are. But what we're allowing now is for you to go in any direction you want, not just the x or the y. So in the direction of u, and one restriction here is that we want u to be a unit vector. And let's give it a specific value, u1, comma u2 or something. So we want to make sure that we're looking at u as a unit vector. So the derivative of f at the point AB in the direction of u is going to be given by and denoted by. So we'll use D for derivative, and capital D is like the standard notation for the main derivative, a derivative, big derivative. And f is the name of your function, and then u is a direction, so we use u as a subscript of d. So this is a derivative in the direction of u of the function, and then we want to evaluate this function at AB. So there's a lot of components here. And we'll write it, and you should look at this and say, oh, that kind of looks like chain rule kind of thing. So we'll write it a couple different ways. We'll write it as the partial of f with respect to x evaluated at AB. And this little dot here is not the dot product, but just a regular multiplication, because this is a scalar. The partial of f with respect to x at AB is a scalar. And we're going to dot it with u1, the first component, not dot, sorry. You're going to multiply it by u1. And then you're going to add the df dy evaluated at AB, and then multiply that with u2. Nope, not a vector, just a scalar. So these are just regular scalar multiplications. Of course, you can peel that apart, and then we can force it to look like a dot product. And if we do that, we get the df dx evaluated at AB, the df dy evaluated at AB, and then dotted with u1 comma u2. And it turns out that this first vector comes up a lot. And yes, this is going to be defined as the gradient. And we say the gradient of f, if we don't have to evaluate it anywhere, it'll be a function of x and y. But in this case, since we want this evaluated at AB, we'll put AB there. And then that u1, u2 is just the u vector. So this is the definition of the gradient. So the gradient is a vector of partial derivatives with respect to the independent variables. Okay? So let's get a visual of this, and then we'll do an example, and then we'll extend this to higher dimensions where we can't visualize it anymore. But while we can, let's take advantage of the idea of being able to visualize it. So let's go to my favorite surface. And somebody standing on my favorite surface. And what we could do is we can look at this plane here. Let's do this in purple. We can look at that plane as a map, two-dimensional map, and then you on the surface being a mountain or a hill or something like that, and that has a three-dimensional feel to it versus a map which only has a two-dimensional feel to it. And then let's say from that point, you're following a specific path. And so the question is, what would happen to your rate of change if you follow that path and that path is pointing in a northwest direction? So if you're following this path in the northwest direction, what's going to happen to you? Well, it turns out that this idea would be the directional derivative. So the question that we can come up with is that find your rate of change in height, elevation, as you move from the point AB on the map from AB to the northwest direction. All right, so if we give these names like z is equal to f of x, y is the name of your function, then we have a function from R2 to R that we're dealing with, and that's being represented by that surface. You're at the point AB, and now we just need to get that, identify this northwest direction So the northwest direction can be given by maybe u is equal to, I don't know, what's northwest? So negative root 2 over 2, comma root 2 over 2. So I was going to say negative 1 comma positive 1, but that's not a unit vector, so you just want to force to make it look like a unit vector. And so divide by its magnitude, which is root 2. All right, so now you have the components, you have the function, you have the point, and then you have the vector. So that the answer to this is this is your directional derivative at the point AB with this as your direction. Okay, so that's the visual involved. But I think we should actually do an example where we're putting in actual functions and actual points and actual directions. Okay? So after we do our example, let's see if we can extend this idea in more dimensions, multiple dimensions, and see what they actually mean. All right, I have some examples set up here, I think. Number 12 looks like it could be a little challenging. Let's see how. Oh no, that's 3 dimensions. Well, let's do that later. All right, let's do number 6. So here they're just asking for a regular directional derivative. We have the function f. We have the point. The point is given by 1, 1. We have a direction, 1, comma 4. Now, what's the issue with the direction here? The direction's not a unit vector, so before you complete your work here, make sure somewhere along the line that you make the direction v into a unit vector. Because just by eyeballing it, it doesn't look like it has a unit length. All right. All right, so that's really all we need to do to prepare for this, aside from taking derivatives and stuff. So let's take derivatives of g, and let's take the derivative of g with respect to the first variable p. And we have 4p cubed minus, now q is constant, so this is going to be a 2p, and then the q remains the same. And we're going to want to evaluate this at 1, 1. So let's evaluate this at 1, 1. And that's going to give us 1 for p and 1 for q. That's just 4 minus 2, right? Next is the derivative of g with respect to q. And so this first term is gone because it's all p. And then the second term is 3q squared. We subtract 1 from the power. And then p squared is constant, so that just stays there. And then if we evaluate this when p is 1 and q is 1, we should get negative 3. So this put together is going to be your gradient evaluated at the point. All right, so that's the first part of your directional derivative. You're going to dot it with u, the unit vector, but we noticed that our direction v is not a unit vector, so let's just make this into a unit vector. Let's find the magnitude of v. The v is 1 comma 4, so the magnitude is 1 squared minus 4 squared. 4 squared is 16. So you add 1, you get 17. And that's just going to be a denominator for your unit vector. So a unit vector now is going to be 1 over square root of 17, 1, 4. You can put that under a fraction, or you can just leave it outside. When you dot it, when you dot things with scalars, remember those scalars just move outside. It's like one of those rules that we have. So our directional derivative, du of g, or dg in the direction of u, evaluated at 1, 1, is going to be the gradient 2, negative 3, the gradient at that point, and then 1 over root 17, a scalar, times 1, 4. So like I said, you can move 1 over root 17, the scalar outside, and then just take the dot product of the vector. So 2 and 1, minus 3 and 4, negative 10. So your slope is negative. That means if this was somehow envisioned as a mountain, and then you look in your map and you go towards 1 comma 4 in that direction. When you take your first step, your height is going to decrease, so you're going to go in a downward slope in that direction. If you go the opposite direction, you should be going up, feeling that same slope. Okay? Does that make sense? All right. In higher dimensions, you simply add more components. And so the formula is going to be the same. Provided that your direction is a unit vector with as many components as n, whatever n is, then it's going to work out to be the same. U unit vector in Rn. Then your directional derivative in the direction of u of that function evaluated at AB, or ABC. And let's just not put the evaluation part. Whatever dimension you're in is as many components as you'll have. And since we have a nice compact way of writing all the partial derivatives with respect to all the independent variables, I can just say the gradient evaluated at whatever that point is, dotted with the unit vector. So this becomes a universal formula for us, regardless of how many dimensions our domain is in, regardless of how many independent variables we have. We just take partials with respect to each of those variables and then assume that your u, the direction you're moving in, is going to be the same dimension. So with that in mind, we should be able to easily do another problem that has higher dimensions. So I think I ran into one of those over here. And let's do one that actually doesn't give you a direction directly. It gives you something where you have to kind of work for your direction. So number 12 has that idea in mind. So here our function is a function of x, y, and z. F of x, y, z equals xy plus yz plus zx. We're starting at the point P is equal to 3, negative 3, 6. Now, they don't give you a direction from P. They give you another point that you're going to go towards. So the direction that you're moving towards is 2, 4, 5. So somehow along the way here, we're going to negotiate what U, the unit vector, the direction that you're moving in, we have to figure out what that is. Okay, so I suppose we should do that first since we've been talking about it, and then we'll figure out the gradient in a little bit. So let's focus on identifying our direction. First of all, we're going from the point 3 minus 1, 6, oh, I'm sorry, 3 minus 3, 6, and we're going towards the point 2, 4, 5. Now, if we subtract them, we're going to get this vector. So let's do the subtraction. 2 minus 3, head minus tail, right? So 2 minus 3, I think that's negative 1. 4 minus negative 3, I think that is going to be a positive 7. And then 5 minus 6 is negative 1. So that's my vector, or at least that's the direction that I want. Now I just want to make this into a unit vector. So the magnitude of V is equal to the square root of, what is this, 49, 50, 51? So the unit vector that you're dealing with is 1 over root 51, negative 1, 7, negative 1. Okay? All right, so the other part of this problem is figuring out the gradient, which is the derivative, and we need 3 of them with respect to x, with respect to y, and then with respect to z. So let's find df dx first. With respect to x, you treat yz as constant, so we have y, x times y, the derivative of that with respect to x is y. And then yz is constant, so that's gone. And then you have z. Okay? And we might as well evaluate this at 3, comma, negative 3, comma 6. So there's no x's in there, but I'm going to put y in for, or negative 3 in for y, and then 6 in for z. So I think I'm going to get a positive 3. With respect to y, I have an x plus z plus 0. Evaluate 3, negative 3, and 6. So I have a 3 plus 6, which is 9. And then the partial of f with respect to z is 0 plus y plus x. So I have a 3, negative 3 plus 3, which is 0. So our gradient evaluated at the point 3 minus 3, 6 is equal to the vector 3, 9, 0. So the directional derivative, the thing that we're looking for, is going to be given by the dot product of these two vectors. So I'm just going to do the dot product and take out the 1 over root 51. and then 3 times negative 1, 9 times 7, oops, this isn't a comma, this is a plus, and then 0 times negative 1, so 60 over root 51. So what does a directional derivative give again? It just gives a slope. So if you were, it gives the slope or the rate of change. So the rate of change here is positive. It looks like if we move from this point to this point, your function value will increase. Okay? So the computation, I think, is fairly straightforward if you know this formula. Only thing you need to really think about is how does this apply to a specific situation. There's one problem that I normally like to give, and that is to find if you're something insect or something flying around in space, and then the temperature of this space is given by a function of 3 variables, depending on where you are in space, and you fly from one point to another point, what is your rate of change of temperature? And so the rate of change, if f was the function for temperature, the rate of change of temperature would be given by a directional derivative depending on which direction you're moving. Okay? Any questions? All right, let's dig deeper into the gradient now, because the gradient seems pretty special. It's like a collection of partial derivatives, so they might mean something. And sometimes the gradient is what people call big D, your big derivative. Sounds like the name of a rapper. Oh, that's heavy D. And that's old school, so you probably don't know it. What? Big. What were we doing again? Oh, gradients. All right. Now, this is this might be a strange thing to look at, but let's imagine this surface. Are you guys sick of this surface yet? Better not be. This is my favorite surface. Yeah, kind of looks like Batman. All right. What are we going to do? Gradient. Let's say we had this point on the surface. And remember that the z value is a z value of the function evaluated at that point. Now, it turns out there's a special set of points with all the same z value. You know what I mean? What do I mean? What do I mean when there's a special set of points? What are the special set of points that have the same z value as this? The plane z equals f of AB. Yeah, you guys are all on the same page. Maybe you guys are all on the same plane. What? So for some reason, if somebody wanted to cut this with a plane, what was the name of that plane again? Z is equal to what? F of AB. Where did you get F of AB? I mean, you're right, Lauren, but I just want to know where you got it from.
Because that is the height of the plane that's parallel to the xy.
So this plane is parallel to the xy plane, and that happens to be the height of the point. Okay, the height of the point is, I think Mimi wanted to call it C at some point. Maybe we should have at some point, but it's at this point called f of AB. And that's just a number. When you put the AB, the actual numbers A and B, into the function x and y for x and y, you're going to get another number. So that's just a number. Okay? So Z is equal to a number. We'll give you a plane, and what happens is that when you cut this plane, you're going to get this constant, whatever that constant is. So there's a couple of things that we can do, possibly. One, we can imagine that we're on this mountain, and then if we go in the direction of that, this, by the way, I don't know if I should have mentioned this, but this, by the way, is a level curve. Do you remember talking about level curves at some point? This is a level curve that you can see down below on your map, right? And that curve goes around the mountain, but you can look at it on your map from a map point of view. And if you go along that curve on your map, what can you say about your directional derivative? The direction that you're going to go is tangent to that curve, yeah. But I'm talking about the directional derivative. If I'm following my map and I see that there's this curve over here that is called a level curve, and I walk along that path, how is my height going to change? Do you understand the question? How is my height going to change if I walk along that path? It's not. Right? It's not going to change. So what are we saying? We're saying that along this path, let's make the path r of t so let r of t be the vector valued function, I'll just say vector path of the level curve. So we know, what do we know? We know something. So if we take the derivative of this, and notice I drew both arrows here to say it doesn't really matter which way you're going along that path as long as it's tangent. What's a vector tangent to this? What's the vector tangent to this curve? What? The derivative. So r prime of t is tangent to r of t, so we could approach this in a couple of different ways. How should we approach it? Oh, we talked about the chain rule, so you guys are comfortable with a chain rule, right? So let's put this idea together. We have, what can you say about f of r of t? So if I do this composition, if I run along this path on my map, right? I'm looking at my map, and there's this path that I can follow, and this path is given by this. If I run along this path, what is happening to my height? Nothing. Can you tell me what my height is exactly? Z, which is equal to what? F of A, B. Maybe I should call it C. All right, let's call it C. Fine, Mimi, fine. The point that it's constant. So what we're saying here is that this derivative, or not the derivative, but the level curve, when that gets put into the function, you have a constant height. So you're walking along this path around this mountain, and you're not going to change in your height. Okay? I want to do something to this equation. When you see this equation, does it make you feel like doing something to it? What do you feel like doing to this equation? What? Taking the derivative. Okay, so this left-hand side looks like eventually it's a function of t. So it's a composition, it's f, which is a function of x and y, but x and y are each functions of t by this parameterization that we came up with. Right? So eventually this is a function of t. So when I want to take the derivative of this, I want to think about this as a straight d derivative. I want to take the d dt of it. I'm out of colors. So I want to take the derivative of both sides. Right? This is a composition of functions, so we talked about compositions of functions already. We can look at this as a gradient dotted with r of t, or we can look at it as something else. But I'm going to write it, maybe I'll write it both ways. So the first thing we want to think about when we're taking a derivative of a composition is the what's this called? The diagram. Now you can imagine it's fx and then x of t, x prime, fy, and then y prime. So I'll write that down, but I want to really get to the next step. So this is f of x, or f sub x, derivative of f with respect to x times x prime plus fy and y prime. But I'm more interested in looking at this as fx comma fy dotted with x prime, y prime. Actually, I'm more interested in looking at it like this. The gradient of f and then I'm going to fill this in. Normally I put AB, right? I'll just put AB. I was going to fill it in with something different. And then the primes is just the r prime. And then let's say I'm going to add on another part to this picture. Let's say when t is equal to 0, you're actually at the point AB. Okay, so r prime of 0. But the point that it's at 0 or somewhere else doesn't really matter. What I have here is the gradient dotted with this r prime, dotted with a tangent vector, tangent to that level curve, is what I really want to get on the left-hand side. By the way, what's the right-hand side? What's the derivative of c, constant? 0. Now, we're looking at this equation. Let's make an observation. What can you say? What?
That r prime is 0.
No. Another one? Okay, close your eyes. Close your eyes. Don't look at the board. A vector dotted with another vector is equal to 0. What do you think of? It's perpendicular. You can open your eyes now. You can close your eyes and then go to sleep. Close your eyes. Oh. Perpendicular. So let's focus on this a little bit more and see if we can say it in words, generalize it, and all that stuff. So the gradient that's that first vector. The gradient is perpendicular to, now before I write the last phrase here, r of t, it's perpendicular to r of t according to our equation, right? I don't want to just put r of t though. R of t represents something a little bit more. So r of t is a vector that's tangent to our curve. Now let's come back. What's our curve? What curve are we talking about? It's this curve r, right? And what does r represent? What is, it's what? What? The path. Okay, some more.
The
Level curve. Okay, so r represents a level curve. And r prime is tangent to a level curve. So we can kind of say the gradient is perpendicular to the level curve. And this statement over here becomes a lot more powerful than just these words that says something is perpendicular to a level curve. It carries really a lot of consequences when we look at these types of functions, and further when we look at higher dimension functions. So let's see what this means. I don't know if I can pull out the old notes that we had where we actually had a level curve going on. How am I going to do this? Let's look at our notes. No, this is a long time ago. Oh, maybe last Monday too?
Not last Monday. What was last Monday? I don't know. The one that was like it's 3.8 or 3.7.
It was after the exam.
Yeah. So that 7 or that 8.
3.7.
I think, yeah.
Yeah, this is the one. What do I want to do? I don't know. Oh, yeah. Well, too late. I'm just going to copy this. All right. So what our statement that we just had, let me take a picture of that as well. Let's think about what this means. So if we take a look at this level curve and I pick any point here, let's pick a point that's on the level curve. Let's pick a point maybe right here. So let's say this thing represented a function. And then I took this function, this mountain, which is a function, and I sliced it up and I brought it down to 2 dimensions like this. And if I'm standing on this point, which direction should I go to represent the gradient? It has to be perpendicular to this thing, right? So I can imagine maybe tangent vectors. Did I do that right? So this would represent your tangent vector, and the gradient would have to be perpendicular to that. Okay? Wait, there's 2 perpendicular directions to go. I wonder which one is our gradient. What? Well, let's think about that later. But the idea is that your gradient is going to be perpendicular. So one of these will be your gradients. So if I'm over here, then my gradient, I know my gradient vector is one of these 2 vectors. Right? So does that make sense so far? So fact number 1 about gradient. Gradients are perpendicular to level curves. Should we do fact number 2, or should we try to look at this from a 3D point of view? 3D? Let's go 3D. Keeping the same piece of information, let's take a look at a function going from R3 to R. Okay? So the question is, what is f of x, y, z equal to a constant? So if I had some function, I can make up a really simple one like x squared plus y squared plus z squared. And if I set that equal to a constant like 1 or 0 or 5, what do I have? What is that thing? It's a what? It's a level. Whenever you set a function equal to a constant, it's a level something, right? It's a level set, usually, is what we call it. So level sets fall into, at least the ones that we're studying, fall into a category of a level curve if you had R2 to R. So this is an example of a level curve in 2 dimensions. And if you have something in 3 dimensions like this is actually level surface. Right? So it's a level surface. So if I take some random equation that has an x and a y and a z in it, I set that equal to a constant and I put it in my graphing calculator program, it'll draw me a surface of something. Okay, so it's a level surface. So let's make this c constant, just so I don't have to write C-O-N-S-T. Just put c. So now, what does this say? If I take the gradient of this, gradient of f, according to this, is perpendicular to a level curve, but now we go to a higher dimension, is perpendicular to a level surface. You know what that does for us? It's no, not vector fields yet. We don't want to mess with that yet. But yeah, we have a normal vector. So since this is perpendicular, the gradient can act as a normal vector. Why do we care about normal vectors? No, what? Not a distance. No. No. You guys are on the same plane? You get path? Direction? Dimension? No. It can act as a normal vector to help us find the tangent plane. I think you guys wanted to say tangent plane, right? Yeah. So this can help us find tangent planes. Should we do a quick example? Let's see. Oh, let's see if there's one in the... Oh, we haven't been checking our answers. Oh, it's all right. Here's one right here. Find equation of a tangent plane and normal line to the given surface. So this is your surface. Like I said, there's a, well, just to make it look like the kind of surface that we are dealing with, we want to make sure that we're identifying a function f and also making sure that that f is equal to a constant. So to make this equal to a constant, I might be interested in bringing everything over to one side, and I don't know if it matters which one goes where. So maybe I'll just put it on the right side, so I'll keep my exponential function positive. 8x, y, z, and then minus x, minus y, minus z. It doesn't really make a difference, but the point is that now it's equal to 0, which is still going to be a surface. If I focus on this, this is really a surface because it's exactly the same as this. And if I plug this into my, like I said, plug this into my graphing program, I'm going to get something. So they give me an actual point, x, y, z point, 0, 0, 8. And then they want me to find a tangent plane, tangent to the surface at that point. And so what do we need for an equation of a plane? We need a point and a normal. So the normal is what we have to find, and that after we just came up with that conclusion from our last discussion, we just easily find the normal by taking derivatives. So partial with respect to x, e to the xyz, the derivative of that is e to the xyz, and then you multiply it times derivative of the power with respect to x, it's just going to be yz. And then take the derivative with respect to x, a derivative of negative x with respect to x is negative 1, and then the other two are gone because they're constants with respect to x. And we are interested in evaluating this at 0, 0, 8. So x is 0, y is 0, and z is 8. It looks like it's going to wipe out this whole thing, right? That's just negative 1. So negative 1 for your x component of your normal. And it looks like it might all be the same. So with respect to y, x and z are constants. And then 0, negative 1, 0 for the derivatives of the rest. So this is all we have. And again, put 0 in for x and 0 in for y. That's going to give you a 0 for the first term. And we're up to negative 1 again. So it looks like it's going to be negative 1 all the way across. But that is going to be your normal vector. So your n is going to be negative 1, negative 1, negative 1. So we're done. We have a point and a normal. We can make a plane. We can make a normal line. We can, I think that's all we can do. But we can do that easily, right? So let's see. Your plane is going to be negative 1x minus 1y minus 1z is equal to the dot product of the point and the normal. So that's 0 plus 0 plus minus 8. Okay? And this looks easy enough to view. Let's get a visual of this. We haven't seen too many graphs coming up lately, aside from my cool surface, right? That's all we've been seeing. So x plus y plus z equals 8e to the x times y times z. So that's how the surface looks like. 0, 0, 8. I need to go. I need to do a little bit more. Zoom. There it goes. It looks like it's going to be right up there. That looks weird. Anyways, let's draw that surface. That's, the plane. So it's all negative, so I'm just going to put x plus y plus z is equal to 8. It's supposed to be tangent right there somehow. Let's change the color of this. And let me see. if I change this going from, instead of minus 8 to 8, let's go from 0 to 16. I don't know if that is more viewable than before. Not what I would have pictured. Oh well. I can't get a nice view of this. Usually if you have these exponential functions, the things get really fast, exaggerated quickly. Oh well. Put it in our notes anyways. We have one more idea that, let me see if I can derive really quickly. And let's look at this from a two-dimensional point of view. Two-dimensional point of view. There's this thing where we're interested in seeing what the fastest rate of change is. And so it's like a calculus problem. We're maximizing something. We're maximizing the directional derivative. And so the question is, this is your directional derivative. And we note that this gradient is fixed. So when we're asking to maximize a directional derivative, we're asking what direction of u will give the maximum value. Okay, so let's see if I can do it real quick. The dot product is defined by some magnitude of stuff times the cosine of some angle between them. So if we imagine this vector, fixed vector v, or not v, I'm sorry, is a gradient. And then we have another vector u. And this is the angle between them, right? So how can we maximize this? So we're trying to maximize this thing. And the important thing to note is, can we simplify this a little bit? Like, what is u? What is the magnitude of u?
1.
This is a unit vector. And this is fixed. And so now maximize cosine of theta. When is cosine of theta going to be a maximum? When cosine of theta is equal to 1 and cosine theta is equal to 1 when theta is equal to 0. So what direction is u going when theta is equal to 0? Direction of the gradient. So df in the direction of u is maximized when u is in the direction of the gradient. And so this is your second very important property of the gradient. First, the gradient is perpendicular to a level curve or a level surface. Second, the gradient is the same direction that would give you the maximum rate of change. So that we will cover in more detail tomorrow. Okay? So if you need to remember two things about the gradient, it's perpendicular to a level curve, and it's a direction of maximum increase. So start saying that a bunch of times, write it down on some index cards and put it in your bathroom walls. See it every day, and then we can tackle some problems.